Hello everyone, I'm Salini and I'm from Flinders University and CSIRO and do my PhD. So today I will be talking about some of the work I have done around water treatment. According to United Nations, by 2050, around 4.5 billion people around the world will face severe water scarcity or stress. So there is an urgent need for finding alternative source of fresh water or innovative water recycling technologies. Water reclamation or reuse is a collection of wastewater, stormwater, recycle it to use it as a drinking, irrigation or industrial water. Now the recycling can be achieved either by engineering techniques or by natural treatments. And managed aquifer recharge or MAR is one of the natural treatment that has gained a lot of attention recently. Now, managed aquifer recharge is the purposeful recharge of water into the aquifer for the later recovery and environmental benefit. And the current practice include MAR is considered as a good option for storage in the water treatment train because it gives a very good public reception and act as a natural buffer, and also sometimes if during the aquifer storage some biodegradable contaminant may get removed. But the managed aquifer recharge requires some treatment of the water before it's injecting into the aquifer, and also some treatment of the recovered water depending upon the end use. Now the current practice include some engineering technologies like the reverse osmosis or ultrafiltration, or disinfection techniques like UV or ozone as a pre and post treatment. And this entire process still make the managed aquifer recharge is very expensive and energy intensive. Now if we can rely on some natural treatments like wetland or granular filtration or rapid sand filtration as an effective technique before as a pre-treatment, then we can skip some of these expensive engineering techniques and make the entire process less expensive. Also, if the research can show that during the aquifer storage, some of the contaminants can be removed while the water is stored in the aquifer, then we can also bypass some of the post-treatment. For example, maybe we don't need any treatment like UV disinfection for drinking water, or maybe we don't need any treatment if the water is going for an irrigation purpose. However, one of the major concerns during the managed aquifer recharge operation is the presence of pathogens in the recovered water. According to the World Health Organization, waterborne diseases are one of the major death that causing all over the world. Millions of people die every year. So, the main pathogens include viruses, bacteria or protozoa. But among them, viruses are considered as the major concern because of their smaller size, like less than 100 nanometer, they may travel a long distance through the aquifer. So it's very important to understand the interaction of these microbes to the sediment surface or in the subsurface environment for us to develop a very effective and economic natural treatment based water recycling technologies. Now, if we look into the processes that happen in micro scale, that means when the water is stored in the aquifer, one of the main processes that happen to the virus is the inactivation in water. And the current MAR guidelines only consider inactivation as the only reliable mechanism that can contribute to virus removal. However, there are also other processes like attachment and attachment of viruses to the solid surface, or they detach back into the solution. And also, while they are attached to the solid grain, they may undergo inactivation. So if the research can show that indeed attachment is the primary mechanism that can contribute to the removal of viruses, then we can use managed aquifer recharge as one of the very economic and sustainable technique in the water treatment train. There are several factors that affect the transport and retention, or we can call here attachment of the viruses in a porous media. This is not only applicable in managed aquifer recharge, any porous system. And these include properties of microbes, chemical composition of water like ionic strength or pH, sediment mineralogy, flow velocity and temperature. So my PhD research mainly focused to understand or gain a mechanistic understanding of the individual and coupled effect of these factors in virus removal. So I will be showing a representative study of my research. The study site I have chosen is a parafield aquifer storage, transfer and recovery. It's a type of managed aquifer recharge practice situated in parafield, and it is a limestone aquifer. So the limestone sediment collected from the site was used as a porous media, and the stormwater collected from the arboreal wetland was also used as the in the experiment. Bacteriophages, a type of viruses which is not pathogenic to human but can infect bacteria, were used as the surrogate for viruses. And all these three viruses share different properties in terms of their size, isoelectric point, which determines their surface charge or hydrophobicity. And we have detected this bacteriophages in the lab using a technique called double layer agar method, which I have established in the CSIRO laboratory. Now, the experiments were conducted as column scale, laboratory scale experiments. A column is 11 centimeter column is actually packed with the collected limestone sediment or river sand. Here, river sand is used as a control. Now, the stormwater is dosed with a non-concentration of virus, which is about 10 raised to 7 viruses per ml, and injected into the column, and the samples were collected in the outlet and injected in the column at a flow velocity of 1 meter per day, and the experiments were conducted at 4 degrees centigrade, and the samples were collected at the outlet and analyzed using double layer agar method. Here I would like to also stress that this technique has a very high detection limit. We can detect up to 30 viruses per ml. Now, the aim of my first experiment was to demonstrate the extent of virus retention in limestone sediment compared to my control, which is the river sand. And here the x-axis shows the time, and the y-axis shows the normalized output concentration of the virus. What that means is C over C00 means complete retention of virus in the column, and C over C01 means the viruses are coming out. There is no retention in the column. Now you can see here in my limestone sediment, I have a complete retention of virus compared to my control. Now, I have already mentioned that I have a very high detection limit for my viruses. So this is in a normal scale. Now, if I show you this in a low scale, of course you can see there are some viruses that are coming out. But don't get confused that this is not a lot. Compared to almost 8.5 billion viruses that I have injected into the column, I have basically retained everything. Almost 2 log retention for my Pikes 174 bacteriophage, and more than 3 log retention for MS2 and PRD1. I also wanted to emphasize that I have done this experiment at 4 degrees centigrade in order to eliminate the inactivation. And I have also kept sample in the stormwater during this experiment duration to make sure there is no, or to measure the inactivation. And I have observed negligible inactivation. So that's incredible. So I can conclude that all these retention that I have observed during my experiment is purely due to the attachment. Now you may ask, okay, now they got attached, now what about release? Are they going to detach back into the solution? Is this attachment is irreversible or reversible? In order to test that, I have challenged my column by injecting stormwater, which is free of viruses, followed by milky water, which is free of salt, and then followed by a worst case scenario, pH 10, and which is in a beef extract, which also contains some protein, so that will mimic the presence of natural organic matter in the natural system. As you can see here, there is no release of any of the viruses. But again, if I show you in a log scale, there are some viruses coming out, but if you look into the mass balance, about 8.5 billion viruses that I have retained in the column, I have less than 0.5%, which is about thousands of viruses that are coming out. So I have concluded that the viruses are either irreversibly attached or they may get inactivated on the surface of the sediment. Now, my previous research as well as other researchers have showed that the presence of calcium in the solution can significantly increase the attachment of viruses in a porous media. In order to demonstrate that, I have conducted my second set of experiment by equilibrating my stormwater in the limestone sediment. So limestone is a calcium carbonate, so it will dissolute the calcium and then get equilibrated. So I will have a high concentration of calcium in my stormwater. Again, you can see here I have complete retention of my viruses. If I show you in a log scale, I have 4.5 log retention of pi-X and more than 6 log retention of the other 2 viruses. Remember that these 2 viruses have about 2 log and 3 log retention in my previous experiment. So this is incredible, considering that I have conducted the experiment in an 11 centimeter column which contains about 50 grams of the sediment. Again, I wanted to now make sure what happened to the release. So I have challenged the column with the same release steps. You can see there is negligible release, and if I show you the mass balance, again, I have even less than 0.04% of the viruses coming out, which is very negligible. So this research now, we assume that when we inject the water in an application scale in the real managed aquifer recharge scale, when we inject the water will passes away from the well, the calcium carbonate will get dissoluted and equilibrated up to a certain concentration. So you will have a higher concentration of calcium away from the well. Now the calcium can act as a bridge because it's a divalent cation, so it can act as a bridge between your negatively charged virus and the negatively charged sediment, and then it can increase or enhance the attachment of virus in the sediment. I also wanted to say that in the managed aquifer research, the velocity, in my previous research, it also showed that the deposition of viruses in a porous media is a coupled process of flow velocity and solution chemistry. So you may have a high velocity near to the well, but as it passes away from the well, the velocity will goes down. That might even increase the deposition in the system. In addition, we have done this experiment in such a short duration. I showed that in less than 12 hours, I have obtained more than 4 log retention of my viruses. And if you now only consider inactivation during this period, it's very negligible. So the summary is that the attachment is a primary mechanism that we can rely on the sustainable removal of viruses in a porous media. So the findings are limestone sediment has a great capacity to remove viruses. The sediment mineralogy was the key parameter influencing the virus attachment and transport in the sediment. Attachment efficiency increased with increasing calcium concentration. The attachment was irreversible, so the attached viruses might have gone inactivated while they were on the surface. So this kind of knowledge, this fundamental research is not only applicable in MR applications, it can be applicable in any system where interaction of microbe to a solid surface is important. So I also like to take this opportunity to say that I have just completed my PhD and I have just submitted my PhD thesis, in fact, yesterday. So that's a great feeling to be here and present. So definitely I like to take this opportunity to ask for any potential job opportunities. I'm more than happy to come and talk to you, any of you that have any opportunity, or you can refer me to someone who have an opportunity. And thank you so much.
So any questions? Let's start there.
What about caverns in the limestone? If the limestone is not a solid rock, if it's corroded underground, it's still going to be affected by trapping the viruses.
Sorry,
so it's flowing like a river underground through the limestone.
Yeah.
It's still going to be affected with removing the viruses.
Yeah, so you mean the limestone is sitting and the particles are moving, so how that can affect?
No,
so
if it's got, if I interpret your question correctly, you're asking if this is still effective in a karst environment where you've got flow through actual channels inside the groundwater.
So it means fractures?
Or very large, effectively fractures, or large dissolved pools. Yeah.
Yeah, so I haven't done any experiments in fractured systems, so that would be the next step to take away. But I would imagine that this process, when we talk about attachment, it is a nanoscale process. So it happens, when the particles comes closer to the surface. So even if it is a fracture system, you still have equilibrated the system with the high calcium concentration, and I would imagine it will still have some enhanced absorption for the viruses towards the surface or the all of the fractures. But definitely that's the next step of this research to take away, to see some field level scale study or fracture system studies.
That was my question, was if we were going to be doing field scale studies. Meg?
That was my question too. Great presentation, by the way. I wondering if you had a feel for longevity of attachment. So it seems that the experiments were quite short term. What would happen in say 20 or 30 years? Once they're attached, do they stay attached?
Yeah, so that's my, what I was saying. Once the particles are attached, they might go inactivation. So they are biological components. So they just basically degrade. So only concern that we have is, okay, once they got attached, they can come back to the solution, and then when you recover the water, they're still alive, so that they can come and infect you. But what if they're inactivated? These are biological particles. They can, their surface contain proteins. So when we talk about this attachment, it's a very strong force. And we're talking about very nanoscale. So they can get ruptured and no more active in a real case scenario. So we're talking about, a big area, and still the attachment would be possible. And I also, if you look into my breakthrough curves, when we do the experiment, it never reaches C/001. It just keep going forever. And these experiments are using 10⁻⁷ virus per ml, which is very, very huge number of virus going into an 11 centimeter column. We're talking about 100 viruses per liter in a real case scenario. So I wouldn't concern about that we will be saturating the attachment site.
Roger?
I guess I had a similar question too. When I saw the limestone was crushed into that small porous media, I wondered what the difference in surface area would be of crushed limestone compared to a natural system. And if you did any back of the envelope sort of calculations to look at whether that changes by orders of magnitude or whether it's just factors.
I would say that I haven't done any of that kind of calculation, but this was a sediment that collected, but this also another, if I have hard time, that was another, like do this type of experiment in a coal holder, the real type of coal, then we can see the permeability effect and all those factors in a real case scenario. But most of my studies were in a sediment or in a porous system, because my aim was to understand the fundamental mechanistic understanding that how the attachment processes happen, and to predict that.
Is it feasible in the lab scale before you try anything outdoors?
Yeah, we had actually a kind of project that came over with flinters, and still probably hoping to do that, a field scale trial that we can go and really inject some bacteriophages into the field and see really what happened here.
But
Well,